Hi there, AP Chemistry. This is Miss Gray and podcast 6.2, Atomic Spectra. So here we get into the fun stuff now. A spectrum, first of all, is simply all the range of frequencies present in the light that you're interested in. So if we have white light, we'd have a continuous spectrum because it's made up of all the colors of light. All colors are possible. So you get this very general sort of rainbow effect, right, from white light. The hydrogen emission spectrum, though, is different. Hydrogen only gives off certain colors, or emits certain colors of light, and this is what we would call a line spectrum. It's called a line spectrum because the wavelengths of energy show up in bands of discrete lines. The lines don't touch, they don't blend, it's one wavelength at a time. So these lines come from the amount of energy from each orbital. So certain energies are allowed for electrons in the hydrogen atom, and that means our change in energy is calculated by this equation. When we're at energy level 1, there's only certain places where the electron's allowed to be, and energy level 2, and energy level 3, and so on. And that frequency, of course, translates into certain wavelengths that we perceive as different colors of light. So the energy in the atom is said to be quantized. And that's where the whole idea of quantum theory or quantum mechanics comes from, is that the energy in the atom is only present in certain amounts, allowable amounts. So we've looked at this simulation before. I'm not going to record it, but we will look at it again in class so that we know exactly what we mean when we're talking about quantum and quantum amounts of energy. But let's look at what Niels Bohr said about the atom. Based on his research, he developed what was known as the planetary model of the hydrogen atom. And it worked reasonably well for this hydrogen atom because it was kind of like a solar system based on the idea that the electron orbits the nucleus in certain orbitals or shells, and that it would stay in that kind of a pathway because it cannot get into a different energy level. He said the electrons would be attracted to the nucleus because of the opposite charge, but because they were moving so fast around the nucleus, they didn't fall into it. They didn't crash into the nucleus because of its inertia as it continued around its orbital path. So these are the basics to the Bohr atom. First of all, only certain energies were allowed. And these were called energy levels. And putting energy into the atom would move the electron away from the nucleus, and that means we would be moving it from what's called the ground state, which is its most stable place, to an excited state where it had more energy than normal and it existed then in a higher energy level. The way to go back from the excited state to the ground state is to get rid of the energy. And when it gets rid of the energy, it gives off light only of a certain wavelength because it's, of course, existing only at a certain energy. So it would be like this. A transition going from level 1, here's our ring 1, to ring 2 would give us a wavelength of energy in the yellow range, a pretty low energy wavelength. But transitioning from level 1 to level 3 would cause more energy to be emitted because it takes more energy to get it farther away from the nucleus. And to go from level 1 to level 4, of course, would be absorbing more energy, so when it falls back to the ground state, where it's supposed to be, it releases this blue wavelength of light. Now, of course, there's other possible types of energy in the infrared and in the ultraviolet, where we would describe what's happening with that electron, how it's absorbing or emitting energy, based on what banding we see in the spectrum. For hydrogen, we always see these 4 colors at exactly the same spot. So hydrogen is very predictable and it's very precise. We all get the same thing every single time. So we can describe the amount of energy that we're seeing by the Ridberg equation. I'm going to check my notes just to make sure that I get this right for you. So the energy during a transition is quantified by this equation, negative 2.178 times 10 to the negative 18 joules times the nuclear charge of the atom squared divided by the energy level of the electron squared. So that's the Ridberg equation. And in this example, or sorry, in this equation, N represents the energy level. Got it? Energy. And then Z is what's called the nuclear charge. In other words, how many positives are there in this nucleus? That's what the nuclear charge describes. And of course, since it's hydrogen, the nuclear charge is +1 because the hydrogen atom is made up of a proton and an electron, and that's it. Right? So it's a +1 charge for the nucleus of the hydrogen atom. That makes this pretty easy to calculate. And since there's only one electron, then N equal to 1 is called the ground state for this atom because the valence electron is in the first energy level. So when the electron is removed from the atom, it's taken so far away that it's no longer associated with that nucleus, then we say the energy level is infinite. And if your denominator is infinite, then energy shrinks to essentially 0. So that's where we define the 0 to be. Notice this is a negative in this equation because this energy is an attractive force. The electron is held to the nucleus by an attraction, so they pull towards one another. That's what makes the sign of this negative. And besides, it would be exothermic when it releases the energy to go back down from a lower level from a higher level to a lower level is going to release energy. So we need to be able to define that as exothermic or negative energy. Now what we're really interested in though is the change in energy. As the electron moves from one level to another, what we really want to measure is how much does the energy change in that transition. So we're looking at delta E, or final energy minus initial energy. Again, this is based on the Ridberg equation, only now we're going to look at some change. So we still have the negative 2.178, 1718, I'm sorry, I have to look. Yeah, 178 times 10 to the minus 18. And since we're dealing with the same atom during this transition, our z squared is still z squared. And yeah, these units are joules, times a change in energy. So I take 1 over my final energy level squared minus the initial energy level squared. So that's the Ridberg equation if we were going to compare two different amounts of energy based on two different energy levels or orbitals where that electron is. All right, same equation, we're just using it twice. So let's do an example so that you can see how this applies. Let's calculate the energy needed to move an electron from its ground state to the third energy level for the hydrogen atom. So we'll work this out together. So we're going to go negative 2.178 times 10 to the minus 18 joules times positive 1 squared for my nuclear charge. And then we have our transition. So the final place, we're going from the ground state to the third energy level. So my final place is my third energy level. I need 3 squared, final, minus initial, which is 1 squared. All right then, get your calculator and let's do this work. Okay, so I got an energy of 1.936 times 10 to the negative 18 joules. And that amount of energy we could then translate into a frequency using the fact that energy is equal to h nu. So we could then calculate the wavelength and predict what color we're going to see because the wavelength is proportional to the frequency, right? So that's how we would apply the Ridberg equation. Let's do another example. Okay, clear the writing. Calculate the energy released when an electron moves from n equals 4 to n equals 2 in a hydrogen atom. All right, so we're going to take a similar approach. The amount of energy released is going to be a change in energy, 2.178 times 10 to the minus 18 joules is going to be multiplied by the nuclear charge of my hydrogen atom, which is just 1, and then we square that, z squared. And my final position, we're going from 4 to 2. So I take my final minus initial. All right, time for math. So I got an energy equal to negative 4.1025 times 10 to the minus 19 joules. And you noticed how I totally ignored sig figs in the last problem. Sorry, I didn't mean to do that. Since these will always be integers, we don't worry about that. Let's just use this for our sig figs. We get to keep 4. So negative 4.103 times 10 to the negative 19 joules. And I want to compare that to the amount we had before. In a transition that went from 3 to 1, we had negative 1.936 times 10 to the negative 18 joules. So to go from a 1 to a 3 takes more energy than going from a 2 to a 4. Does that make sense? Seems like a smaller transition. Well, the leap from ground state to anything else will always be bigger than the outer energy levels. So to get from a 1 or from its ground state to any other place is going to always cost more energy, even though this transition is a difference of 2 and this is a difference of 2. Going from 2 to 4 will be smaller, and going from 4 to 2 will be smaller than going from 1 to anything else. Let's look at our next example, shall we? We'll just cruise right on through. Clear that writing. Calculate the energy released when an electron moves from energy level 5 to energy level 3 in, now we're dealing with a helium plus 1 ion. All right, so normally helium has 2 protons, 2 neutrons, and 2 electrons zipping around that nucleus, right? But a helium plus 1 ion would be a helium where we've removed one of these electrons, and now we have only one left. So this is going to have a different nuclear charge. The Ridberg equation is still the same, 2.178 times 10 to the minus 18 joules. And now our z squared is going to be 2 to the second power because helium has 2 protons. That's how we describe nuclear charge, the number of protons. And then our final position is a 3, so 3 squared is 9. And our initial position was a 5, and so that's 5 squared is 25. All right, calculator time. So here's what I got. Negative 6.1952 times 10 to the minus 19 joules. And if we kept 5 sig figs, 1, 2, 3, 4, 5, we just get to keep them all. All right, well that's it. That's how we use the Ridberg equation, and you're going to get lots of practice at this when you do the flame test experiment. Last year you did the flame test and measured color in wavelengths. Now we're going to take the wavelength and change it to energy so we can apply the Ridberg equation and predict what transitions we're seeing, which energy level are we going from and to. So we want to know, when is this true? When does the Ridberg equation apply, and when does the Bohr model work? Well, here's the trouble. It only works for hydrogen atoms and other monoelectronic species. So anything that has only one electron will work for this model, because then we wouldn't have any attractions or repulsions for the two electrons in the same orbital. You see, that could become a problem, especially if we have effects of shielding. So those other interactions complicate the math significantly. The Bohr model only works for hydrogen, and the negative sign is based on how we define potential energy. To increase the energy of the electron, you would have to bring it closer to the nucleus, and that's an attractive sort of force. The maximum energy that an electron can have, then, the most positive that it could be. Let's define maximum as, oops, I clicked something there, sorry. I don't know how to get rid of this. Ah, there we go. Okay, so the most positive the energy could be would be 0. Because then once the energy is 0, you're at an infinite distance from the nucleus. And so you'll never get an actual value that's positive, that's greater than 0. But the maximum energy defined as the most positive would be 0 for this electron. So the Bohr model works only for hydrogen atoms very well, because hydrogen atoms don't have the same effects of shielding and other attractions and repulsions of positives and negatives. It's just one positive and one negative. The Bohr model only works for hydrogen. And we also know that electrons don't move in circles. So the Bohr model, or the planetary model, just doesn't really fit what we know to be true of atoms. The quantization of the energy is correct, but not because they're circling like planets. So there's more to this story than just the Bohr model. If the experiments don't verify the theory, then the theory has to be modified, and the Bohr model of the atom was modified to fit the evidence. So in our next podcast, we're going to look at the quantum mechanical model of the atom so we can describe what best fits the evidence that we know today. So I'll see you guys soon.